The first law of thermodynamics. Before working through the first law of thermodynamics, we need a closer look at heat and work. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. Let's start with the concept of internal energy of a system. We have already seen that the internal energy of a system is simply the sum of the kinetic energies associated with various random motions of its molecules. Let the letter U be the internal energy, and the internal energy of a given mass of gas depends on its state described by specific values of pressure, volume, and temperature. Now we will see what are the ways to change the internal energy of a system. Let us take as our system, for simplicity, a gas confined to a cylinder with a movable piston. There are two ways of changing the state of the gas, and hence its internal energy. One way is to put the cylinder in contact with a body at a higher temperature than that of the gas. The temperature difference will cause a flow of energy, heat, from the hotter body to the gas, thus increasing the internal energy of the gas. The other way of changing the internal energy of the gas is to push the piston down, that is, to do work on the system. Calculating the work done in an isobaric change. An isobaric change is one which occurs at constant pressure. We now will find out how to calculate the work done by the gas or on the gas by the surroundings. Consider an ideal gas at a pressure P enclosed in a cylinder of cross-sectional area A. When the pressure of gas pushes a piston out, then the gas expands and pushes the piston a distance delta x. The work done by the gas during this expansion is given as follows. The work done during expansion is the force times distance delta x, but the force is pressure times area. Therefore, the work done by the gas is given by pressure times change in volume. An isobaric process appears on a PV diagram as a horizontal line. The work done by the gas is represented on the PV diagram by the rectangular area under the isobaric path on the diagram. If the gas expands, the change in volume is positive, and the work done by the gas is positive. When the gas is compressed, the change in volume is negative, and the work done is negative. We have seen that the internal energy of a system can change through two modes of energy transfers, heat and work. Let delta Q, heat supplied to the system by the surroundings. W, work done by the system on the surroundings. Delta U, change in internal energy of the system. Nothing quite exemplifies the first law of thermodynamics as well as a gas trapped in a container with a tightly fitting movable piston. We will assume the piston can move up and down, compressing the gas or allowing the gas to expand. When heat energy is applied to the gas, the temperature of the gas increases. Then work is done by the gas expanding to move the piston, resulting in a change in the internal energy of the gas. According to the law of conservation of energy, energy can neither be created nor destroyed, so the amount of heat added to gas must equal the work done by the gas plus the increase in internal energy. The first law of thermodynamics is the application of the conservation of energy principle to heat and thermodynamic process. The first law of thermodynamics states that the change in internal energy of a system equals the net heat transfer into the system minus the net work done by the system. Pay attention to the following exercise. The figure illustrates the problem. Water boiling at constant pressure. Energy is transferred from the thermal reservoir as heat until the liquid water has changed completely into steam. Work is done by the expanding gas as it lifts the loaded piston. How much work is done by the system during this process? The system must do positive work because the volume increases. We calculate the work done by multiplying pressure by change in volume. How much energy is transferred as heat during the process? Because the heat causes only a phase change and not a change in temperature, we use the latent heat formula. Because the change is from liquid to gaseous phase, L is the heat of vaporization. The change in the system's internal energy is related to the heat. Here, this is energy transferred into the system, and the work by the first law of thermodynamics. Heat engines. One of the concerns of thermodynamics is the efficiency with which heat can be converted into work, and the process of continuously converting energy into work is difficult to achieve. But it can be done using a heat engine that operates through a cycle of change. A cyclic process is a series of transformations that take a gas back to its original state. The principle of a heat engine can be represented by an energy flow diagram and by a pressure volume diagram. We can think of the system as being a steam engine in which the working substance is water enclosed in a cylinder with a frictionless movable piston. Let's see the heat engine works through one cycle. When energy Q1 is supplied to the water from a hot reservoir at temperature T1, the temperature is increasing, but the volume is not changing, so no work is done. The water first evaporates into the steam boiler. The steam expands against a piston and moves the piston. The volume increases, so work is done by the steam. This will stop as soon as the steam pressure is equal to that of the surroundings. The steam now needs to be returned to its original state before it can do further work. This can only happen if some of the energy Q2 that was initially absorbed is rejected to a cold reservoir at lower temperature T2. The internal energy must go down. After the steam is condensed with cooling water, it is compressed back to its original volume, and it returns to the boiler, and the process is repeated. When represented on a PV diagram, the process forms a closed loop. The work done by the engine for a cyclic process is the area enclosed. Because the working substance goes through a cycle, always returning to its initial thermodynamic state, its initial and final internal energies are equal, so the change in internal energy is zero. From the first law of thermodynamics, we get The last equation shows that the work done by a heat engine equals the net energy absorbed by the engine. The thermal efficiency, eta, of an engine is defined as the ratio of the work it does to the amount of heat energy put in, that is, Q1. Pay attention to the following exercise. We can find the engine's thermal efficiency substituting Q1 and Q2 into equation for efficiency. To calculate the work does this engine do in one cycle, subtract Q1 from Q2. To calculate the average power output of the engine, we multiply the work done by cycle by 4 and divide by time. The Carnot cycle. In 1824, in an effort to understand the efficiency of real engines, a French engineer named Sadi Carnot described a theoretical engine now called a Carnot engine that is of great importance from both a practical and a theoretical viewpoint. He showed that a heat engine operating in an ideal reversible cycle between two energy reservoirs is the most efficient engine possible. Such an engine establishes an upper limit on the efficiencies of all real engines. Carnot's theorem can be stated as follows. No real engine operating between two energy reservoirs can be more efficient than a Carnot engine operating between the same two reservoirs. The cycle consists of two adiabatic and two isothermal processes. The process from A to B is an isothermal expansion at temperature T1, in which the gas is placed in thermal contact with a hot reservoir at temperature T1. During the process, the gas absorbs energy Q1 from the reservoir and does work in raising the piston. In the process from B to C, the base of the cylinder is replaced by a thermally non-conducting wall and the gas expands adiabatically, so no energy enters or leaves the system by heat. During the process, the temperature falls from T1 to T2, and the gas does work in raising the piston. In the process from C to D, the gas is placed in thermal contact with a cold reservoir at temperature T2 and is compressed isothermally at temperature T2. During this time, the gas expels energy Q2 to the reservoir and the work is done on the gas. In the final process, from D to A, the base of the cylinder is again replaced by a thermally non-conducting wall and the gas is compressed adiabatically. The temperature of the gas increases to T1, and the work is done on the gas again. For a Carnot engine, the following relationship between the thermal energy transfers and the absolute temperatures can be derived.